All right, welcome to Chapter 6. We're going to be looking at Section 6.3. We'll do this over a series of 3 videos, so we'll call this one Day 1. And the whole section is about binomial and geometric random variables. On Day 1, we'll spend some time just investigating the binomial distribution. So, in the objectives for the section, for video 1, we're going to determine whether the conditions for using a binomial random variable are met. There are 4 conditions that we will have to investigate. We'll learn to compute and interpret probabilities involving binomial distributions. On Day 2, so Day 1 will be right here. On Day 2, we'll learn to calculate the mean and standard deviation of a binomial random variable. And then on Day 3 video, we will look at the geometric random variable. And then, time permitting, we'll look at the normal approximation of the binomial, even though that's not required for the AP statistics exam. So, the binomial setting. What is a binomial setting? Well, when the same chance process is repeated several times, we are often interested in whether a particular outcome does or doesn't happen on each repetition. So I always like to think of like shooting baskets. If I asked you to shoot 10 baskets in a row, that is a chance process repeated several times. And I might be interested in what's the probability you make 7. So look, I'm interested in a particular outcome and whether it happens or doesn't happen. So some random variables count the number of times the outcome of interest occurs in a fixed number of repetitions. So again, I had a fixed number of repetitions. I had 10 that I was going to make you shoot. So these are all called binomial random variables. And a binomial setting arises when we perform several independent trials, like the basketball example. Each shot is independent of the other. So we perform several independent trials of the same chance process and record the number of times that a particular outcome occurs. So I'm looking at that problem I was trying to get 7. So, but to be a binomial setting, there must be four conditions that must be there in that setting. And the first one is it binary? Is it binary? So the possible outcomes of each trial can be classified as either a success or a failure. It must be independent. Trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of any other trial. In other words, the first one does not affect the second one. The second one does not depend on what happens in the first. The number. Well, the number of trials, we'll call that N, of the chance process must be fixed in advance. It's like my basket example. I'm saying I'm going to make you shoot 10 free throws. That's fixed ahead of time. And then the success, we have to have the same probability of success in each trial. So maybe I'm a 75% free throw shooter. That probability remains constant, remains the same for each free throw that I take. So a little mnemonic device to remember a binomial setting. B-I-N-S. So remember, in a binomial setting, your bins. So here's another example. Consider tossing a coin n times. Each toss gives either heads or tails. Okay, so there's our binary piece right there. That we've got either heads or tails. Knowing the outcome of one toss does not change the probability of an outcome on another toss. So there's our independence. We're going to toss a coin n times, so that's our fixed number of trials. So we'll have to fix that ahead of time. Somebody will tell us how many we're going to do. And then if we define heads as success, then P is the probability of a head is 0.05 on any toss. Is that this success is constant throughout. Okay, so that's constant, no matter when I flip the coin. So the number of heads in n tosses, this is a binomial random variable x. The probability distribution of this is called a binomial distribution. So again, in the green box, the count x of successes in a binomial setting is a binomial random variable. So the count So you could get 0 free throws made, 1 free throw made, 2 free throws made. Or in this problem, heads, I could either get 0 heads or 1 head or 2 heads or 3 heads out of how many I'm tossing. The probability of distribution is a binomial distribution with parameters n and p. So sometimes we abbreviate that, like normal, we'll go b n comma p to indicate a binomial distribution with n fixed tosses and the probability of each of those individual tosses. So the possible values of x, the possible values of that random variable are always whole numbers. So when I flip a coin or shoot a basket, I'm either going to get 0 or I'm going to get 1. I'm not going to get fractions or decimals. So let's just look at an example. In a binomial setting, we can define a random variable, say x, as the number of successes in n independent trials. We're interested in finding the probability distribution of x. So in this problem, we've got each child of a particular pair of parents has a probability of 0.25 of having type O blood. Okay, so there's our probability. Okay, and that's going to remain constant throughout. It says genetics say that children receive genes from each of their parents independently. Well, there's another one of our key phrases there. We want independence. If these parents have 5 children, so there's going to be our fixed number of trials. We're going to have 5 kids, no more, no less. The count x, there's our random variable, children with type O blood, is a binomial random variable with n equals 5 trials and probability 0.25. So again, we could define that, go like this, just shorter. We can say b of 5, comma, 0.25, just to shorten that up mathematically. So in this setting, a child with type O blood is a success. We want to find somebody with type O blood. And a child with another blood type is a failure. So what I want to do is I want to find the probability of having exactly equals 2. We want to have exactly 2 children out of 5 that have type O blood. Well, here's one way that could happen. I could have my first 2 kids could have type O blood, and the next 3 don't. So the probability they have type O blood is 0.25. This one is 0.25. And each of these other 3 don't have type O blood, so their probability is 0.75. Shortened up, this is 0.25 squared, because there's 2 kids with O blood and 3 kids without O blood. And because they're independent, we can multiply these all, and there's that probability for this specific event. But wait a minute. There are a number of different arrangements in which 2 out of 5 children can have type O blood. It doesn't mean the first 2 and the last 3. It can mean all of these different types, all these different events, all have 2 kids with O blood and 3 kids without O blood. And each of these different arrangements would have that probability. And you can see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these different possibilities. Again, this was the same one right here. So to calculate the probability, I'd have 10 of these different arrangements of 2 kids with O blood, 3 without O blood. And that'd be my probability of getting exactly 2 kids amongst 5 that have type O blood, so roughly about 26.37%. So in that previous example, any one arrangement of the 2 successes and 3 failures had the same probability. That's true because no matter what the arrangement, we'd multiply 0.25 twice and 0.75 3 times. So what we're looking to do is generalize this statement into something that we can use for any given binomial situation. So if I want to find the probability of any specific event, I'd have to find, in other words, the probability exactly of k successes in n trials. And the last problem was 2 successes in 5 trials. We'd have to take the number of arrangements, and in our last problem that was 10, times the probability of success, and how many of those we wanted, that's the k. And then here's our probability of failure, which is just the complement of success, and then the number of failures we'd have to have. Now, the calculation of this number of arrangements can be shortened by just doing what's called a combination. And our formula for finding that, for finding the number of ways of arranging k successes among n observations, is given by this formula right here. And I'll show you a faster way to do this on the calculator as well too. But this is called a combination. You got n choose k. So in other words, out of n observations, we want k successes. We're working this formula longhand. We do n factorial. And if you don't remember what factorial is, so like if I had the number 5 factorial, that would mean 5 times 4 times 3 times 2 times 1. So it's always just whatever number you're at times the descending order of those. So not necessarily have to memorize this formula because we'll end up just using our calculator for this. And just out of definition, just so you know, 0 factorial is always 1. Okay, so put it all together. Here's our binomial probability formula. And again, that the binomial coefficient, this part right here, calculates the number of different ways in which I can have k successes and n minus k failures. So again, this is the number of arrangements of the k successes. That's the probability of k successes. And this 1 minus p, that is the probability of n minus k failures. And many times this 1 minus p, we'll just write it as q, just to be a little shorter. So how do we find these binomial probabilities? Well, state the distribution and the values of interest. So specify that it is a binomial distribution with a number of trials, a specific set finite number of trials, the success probability, so the probability of success, and then the values of the variable clearly defined. So we're looking at, are we looking for a specific value or are we looking for a range of values? And then we just perform the calculations. And as always, show your work. So in doing that, we do one of the following. You can use the binomial probability formula that we just had on the previous screen, or we'll show you the calculator usage here as well. And then obviously answer the question. So, finishing up with our problem here, we've got each child of a particular pair of parents has probability of 0.25 having type O blood. Suppose the parents have 5 children. We want to find the probability that exactly 3 of the children will have type O blood. So, there's our variables. X is the number of children with type O blood. And we have 5 total children. Probability is 0.25. So we're going to choose, if we have 5, choose 3. Probability of success is 0.25, getting somebody with O blood. We want exactly 3. This is the probability of failure, and we want exactly 2 of those. And if we do the math on this, this is the answer we get. Down below, if we want to find the probability of X is greater than 3, so we want more than 3 children, we've got to find the probability of 4 and the probability of 5 children having type O blood, and add those 2 probabilities together. So you can see this gets to be a little bit of work if we have inequalities involved. So in this problem here, there's only a 1.5% chance that more than 3 children out of 5 would have type O blood. And you should be surprised if you had 2 kids out of 5 that had type O blood. I'm going to do a supplementary video showing the calculations on the calculator for this, and we'll put that one in between. We'll call that one Day 1B. Okay? And then we'll talk about the homework there. Okay? So to be continued, please move on to the calculator video.